Good afternoon, everyone. So today we're gonna have a 2-hour tutorial. The first one is for deep neural network basics. The next one is deep learning applications to computer networks. So actually, we have 2 tutorials, right? The first one is for the basics. The second one is for the applications. So then in the main program, I said that we're gonna have 2 tutorials and 1 hour for each. However, in this case, I would like to have 2-hour tutorials entirely. It means that we may have 40 minutes for the first one and a little bit more than 1 hour for the next one. So we have some flexibility, okay? So let me start with deep neural network basics. So thank you for coming today. Thank you for your time today. 안 되는데? 아마 이게 편집 사용으로 돼 있으면 그렇게 될 수도 있어요. 네. 아닌데? 자대로 되는데? 프레젠테이션으로. 네. 이걸로 해야 되나요? 그럼 어떻게 해? 이걸로. So, instead of pointer, let me use this one, okay? So, I will stand here. So, we're gonna start with deep neural network basics, okay? So, actually, deep learning has a lot of attention, maybe for 5 years. So, in 2016, on March, we have one big event. So, AlphaGo player at the time. So, from that time, people start to have some interest on deep learning or AI applications. So, but from that time, someone said that it is just kinds of applications, it's just kinds of big trends. But however, last year in ACM, there is one Turing Award reception for 3 professors, 2 professors and 1 doctor, and Professor Jeffrey Hinton and Yoshua Benjor and Dr. Yan Lukun. So those are all pioneers in deep neural network or deep learning research topics. That's why I believe that from the time, every research society start to say that this is not only for the applications, but for huge research topic. So I believe that from the time, everybody start to agree that deep learning may have a lot of impacts on every single research topics. So before starting, let me summarize what is the main subtopics in machine learning. So actually, we in newspapers or non-technical articles, we are mixing the terms. So AI, machine learning, deep learning, those are used at the same time. However, in technical papers or technical manuscripts, we have some distinguish between AI, machine learning, and deep learning. So AI is the huge research topic. It has reasoning, it has computational logic, it has probabilistic graph model or something like that. But inside there, we have one topic that is called machine learning, which is also called statistical learning or computational learning. So machine learning has 3 subtopics. As you can see over there, we have unsupervised learning, we have supervised learning, lastly, we have reinforcement learning. So unsupervised learning, the supervised learning means that we have one learning architecture. On top of the learning architecture, we have a lot of data. So instead of on top of the data, we also have the labels. So suppose that we want to design one classifier. So in order to train the classifier, we will gonna put a lot of data. So suppose that we want to make a classifier which can distinguish between apple and banana, then we will gonna put a lot of banana data or apple data. But with the data, we have to put the labels as well. Then the classifier can distinguish between apple and banana if it has some new arrivals. But in unsupervised learning, it has data, but it doesn't have label at all. So it has only data. That's why based on the data itself, we have to do classification, we have to do data mining, we have to do a lot of stuff. That's called unsupervised learning. That's why the main difference between the supervised learning and unsupervised learning is that in supervised learning, we have labels. In unsupervised learning, we don't have labels. There is a big difference between the supervised learning and unsupervised learning. So in below, you can also see the reinforcement learning. It has different segmentation. So suppose that you want to make an action and you want to make an action based on the given statement. Then you have to consider the reinforcement learning. So in AlphaGo Go player, we have state. Okay, and then we're gonna make an action on top of the state, and then the state changes, and then in that case, our opposite side will make another action, then state will change again, and then in that case, I will play again and again. That's why in that case, if we have sequential action which aims at the optimal reward eventually, then we will consider reinforcement learning. Okay, that's why reinforcement learning is another topic we can consider in deep learning research society. So. In order to, so in these kinds of classification or overview, our deep neural network related researches are all related to supervised learning. If you are studying about kinds of optimal action or optimal control or something like that, then you will gonna study more about reinforcement learning. Okay, so for only 1 hour, we will focus on the supervised learning. For later, we will focus on the reinforcement learning. Okay. So this is the basic deep neural network architecture. So on right hand side, you can see neural network architecture. You have input here, you have output here. So input, it has 5 dimension, it has one dimensional vector, and it has 5 elements. It means that, okay, we will gonna get any kinds of input which has 5 elements. Okay, in output, you have an output as on 1 dimensional vector. So between input and output, you have model. Neural network model, and as you can see here, you have 4 hidden layers. You have 7 units in each hidden layer. So in this case, you have to define this model at first before allocating some data on top of this neural network architecture. So if your classification task is very complicated, then you need more hidden layers. You need more units in each hidden layer. But if your classification task is very simple, then you may not need a hidden layer. You may need a little number of units. So the complexity of the neural network architecture depends on your task complexity. Okay. So the first stage for deep learning computation is that you have to set up deep learning model. So you have to decide whether you will gonna use multi-layer perceptron, convolutional neural network, recurrent neural network, GAN, or customized network architecture. Or you have to also define how much layers you have to use, how much unit you have to use. You have to define the dimension of input and output, and so forth. So depending on the learning direction or learning objectives, you have to define your cost function, or you have to define your optimization. Okay, so usually you are using gradient descent optimizer, Adam optimizer, or something like that. But in some specific cases, you need your specific optimizer. So you have to select optimizer as well. Once you set up the model in your first stage, then you have to start your training with some data. So as I mentioned here, we need large scale data. Suppose that we have 1,000 data. It may enough or it may not enough. It depends on, okay? Sometimes our task might be very complicated, then we need more and more data. If our task is very simple, then we may need a very small number of data. So it depends on your task complexity. So here, once you set up the model in the first stage, then you have to train. So in order to do the training, then you need a lot of data. So suppose that you want to design your classifier, which can distinguish between apple and banana. So in that case, you have to put a lot of banana image here, then you have to put label here as well. So after your allocation of your banana data, you start to put your apple data. So you will put a lot of apple images here, and then you will put a lot of labels for apple. And that's it. So here, as I mentioned here, our input is data, our output is labels, okay? And then learning means that you have to find weight parameters here. Depending on the given data, given images, then you will gonna train your weight in yellow circles. So that's called weight. That's why learning procedure is called weight of tests for cost function minimization. So here, cost function means that it is the difference between the actual data and your parameter data. Okay, that's why your parameter should be trained in order to be very similar to your real data, real labels. So once you are done, then your yellow circles has some parameters. Then, so once you are done, your yellow circles may have some parameters. So in that case, you will put this model on top of this real-time system. So in real-time system, it has IID random arrivals. So the arrival can be converted to this kinds of vector. Then this vector will get into this neural network architecture. Then you will gonna have matrix multiplication, several matrix multiplications, and nonlinear function applications. And then you will derive one output vector. So this output vector will be your estimated result. So you can say that this is apple, this is banana, based on the trained parameters. So here, so the procedure is called inference or testing. So testing will be done with real-world execution. Okay, then your input will be real-world data arrival, as you can see over there. Your output is your inference. So in this neural network architecture, one major problem is overfitting. So so when you look at your neural network architecture, even though the code itself is very perfect, is 100% perfect, or if your logic is 100% perfect, but you may have some degraded result. That is called overfitting. So in this case, everything is perfect, except one fact that you have small number of data. Suppose that you wanna make a bet, you wanna make some comfortable bet, which is very comfortable and which costs the human factors a lot. So in that case, you wanna make this kind of very nice bet. So in that case, you need a lot of data, as I told you before. In order to train your model, you need a lot of data. But suppose that you only have one data, then your model will look like this one, because the model is very similar to this shape. So in that case, this shape might be very comfortable only for this person, not for the others. So then that is called overfitting. It means that your model is very suitable only for little number of data. Okay. So overfitting will happen when you do not have enough data. Okay. So everything is perfect. Okay. Your code is perfect. Your training procedure is also perfect. The only problem is that you do not have enough data. That's why it's very hard to check whether your overfitting is occurred or not. So in your lab, your cost function is well minimized. It means that this shape is very similar to your sleeping shape. Then you can say that, okay, the cost function value is very small. That's why your model is very good. However, when you put this one outside and you want to sell this bet, then the performance may be very low. It means that you have overfitting. Okay, so overfitting is very difficult problem. That's why you have to deal with this one very carefully. So in conventional neural network, as you can see over there, our input is always one-dimensional vector. This is a very huge limitation in neural network training or neural network architecture. So in that case, people start to think that you need some technique which can accept high-dimensional input. That is called CNN architecture. Okay. So in CNN, one big difference between the CNN and multi-layer perceptron is that it has high-dimensional input data. So if you want to use deep learning architecture for image processing or video processing, then your input will be two-dimensional images, or your input is a three-dimensional video image. So in that case, you need high-dimensional input acceptance. So in conventional neural network, it is not allowed because it only accepts one-dimensional vector. But in this case, you can accept two-dimensional, three-dimensional, or even higher dimensional input vectors. That's why CNN is very powerful nowadays. That's why people generally say that CNN is very useful for image processing or computer vision applications. In RNN, it can consider the time series information, because this is the input vector of the neural network, this is the kinds of neural network, and this is output vector, okay? And then the trained parameters here will be delivered to next time step neural network and so forth. That's why it can consider time-related information. That's why this is very useful for time series estimation, time series forecasting, or something like that. So in deep learning, one big application is vision or image processing. So it can be generally used for the object recognition. It can be used for the style transfer. When you take one digital camera image, just like this one, and then on top of this image, you can transfer this image into this one, or this one, based on the artist painting characteristics. So this is one painting, this is the other painting, this is the other painting. In your deep learning architecture, it can understand the style of this painting. And then you will apply the style into this digital image. Then you can convert this image into this one, okay? This is called style transfer. If you want to use deep learning or computer vision applications for autonomous driving, then you have a camera in front of your autonomous vehicle. So in that case, the camera will accept a lot of images in real time while driving. So then the image may have some blurs or noise or something like that. That's why we need deep learning or denoising techniques. So maybe 20 years ago or 15 years ago, we had a lot of technique for deep learning or denoising based on statistical method. But nowadays you are doing these kinds of tasks based on the deep learning architecture. The last one is the super resolution. Super resolution means that suppose that you have 10 by 10 image data, but you want to increase this one, so maybe 1,000 by 1,000. Then you will have a lot of large pixels which can degrade your resolution. So then, even though the size is up, then you have to improve your resolution. That's called super resolution. Okay. Next application is speech and language recognition. So you can do speech recognition, you can do language translation, you can do information retrieval, such as search engine or something like that. These are all related to language-based deep learning. So from now on, I would like to introduce basic computational procedure for deep learning computation. So in this toy model, you have two hidden layers. You have only one output layer, and you have only one input. So in conventional basic neural network architecture, as I told you that we have one-dimensional vector, just like that. Okay. So this is our one-dimensional vector. So in this one-dimensional vector, you have three elements, okay? So in your two hidden layers, you have 4 units. This one also has 4 units, okay? So as I told you before, your input is one-dimensional vector. It has 3 elements. In output, since you have only 1 unit, it has only 1 data, just like that. So this is one-dimensional vector, 1 by 1. So this is your input and this is your output. Suppose that this neural network architecture is for the classification between apple and banana. So when you put apple images just like that, then your apple image will be one-dimensional 3 elements. And if this is 1, it means apple. If this is 0, it means banana. You can make label just like that way, which is one very simple example. And then you have 4 units in your first hidden layer. Since this is 1 by 3 matrix, each unit has 3 by 1 weight vector. So then you have to do the multiplication. So this is 1 by 3, this is 3 by 1. That's why when you are doing the linear combination, then you have only 1 value. So 1 value will be added with this bias. Then you have 1 value. This is the 1 value from this first unit. So for the second unit, it has same computation procedure. Since this is 1 by 3, this has 3 by 1 matrix. Then you are gonna do the linear combination, and then you are gonna add this bias. Then you have only 1 value. This will be this second element. For this third unit, it also has 3 by 1 matrix in order to do the linear combination with this input, and then you have only 1 bias. And then you have this value. Lastly, you also have 3 by 1 matrix because you wanna do the linear combination with this 1 by 3, and then you have 1 bias in order to do the addition on top of the result. Then you're gonna get this result. That's why the result of this first hidden layer will be 1 by 4 matrix, okay? So for this second hidden layer, you have 4 by 1 matrix because you wanna do the linear combination with this given input. Because this is 1 by 4, it has 4 by 1. So even though they look similar to each other, in hidden layer 1 and 2, their exact mathematical formulation is different. This is because this is 3 by 1, this is 4 by 1. Okay, they are not same to each other. You have 1 by 4 matrix as an input of this second hidden layer. It has 4 by 1 matrix and only one bias. Then it will be this first value. And the other unit has same computation. That's why you have 1 by 4 matrix as an output of this second hidden layer. And this will be input of this output layer. That's why this one has 4 by 1 because its input is 1 by 4. And then you have one bias. So as you can see here, if you have more and more hidden layer, you're going to do matrix multiplication, bias addition, and then you have a nonlinear function on top of that. Then now you have to understand why we have to do these kinds of calculation. So when you study about machine learning, at first you're going to study about linear regression. So as you can see this here, you can easily understand why it's the linear regression. So you have 3.3 samples. Based on these 3 samples, you want to derive one linear curve, linear equation, which can represent these given samples correctly. But interpolation has different meaning. So you may study about interpolation in numerical analysis class. So in interpolation, when you have 3 samples, then you want to get one curve which can exactly go through every single samples in this space. So if you have only 2 samples, then you're going to have one linear curve. If you have 3 samples, we're going to have second order equation and so forth. That's why when you have when you want to do the interpolation with the polynomials, you may think that okay, since we have 3 samples, you need a second order equation, second order polynomial equation. And then since you have 3 samples, you're going to put 1 by 10 here, you're going to put 2 by 15 here, you're going to put 3 by 40 here, and then you will derive 3 equations. When you solve these kinds of 3 equations, then you're going to derive these kinds of blue parameters, coefficients. Then you're going to get the exact second order equation. This is called interpolation when you study during numerical analysis class. So this kind of procedure is related to neural network training. So as we studied before, when you have this kinds of neural network architecture, when you have an input just like X, which is red one, you have output which is green one, capital Y, and then you want to do the multiplication with W of first hidden layer, and you want to add this bias, and then you can take the nonlinear function. And then based on the result, you're going to do the multiplication with W2, and then you're going to do the addition with the bias 2, and then you will take the nonlinear function. And lastly, in output layer, you're going to do the multiplication with W sub 0, and then you're going to do the addition with B sub 0, and then you take the nonlinear function. Okay, so this is the mathematical procedure of the neural network architecture. But now, as I told you before, you are going to put a lot of data here, and then you are going to put a lot of labels here. Then you will derive the exact value of these parameters. So in this slide, what I want to say is that this kinds of neural network architecture training is very similar to interpolation. Because in interpolation, you have a lot of sample. You want to find the function which can follow the exact tendency of the samples. But in this case, you will make the interpolation related function at first, and then you want to find these values, okay, by allocating a lot of data as an X and Y. That's why this is called functional approximation, because you want to find the function which can define the relationship between X and Y. So in many deep neural network or deep learning textbook, which are talking about the mathematical meaning of the neural network, and then you can always find the sentence that is called functional approximation. Okay, and this kind of nature is also considered in reinforcement learning as well. So in reinforcement learning, as I told you before, you will see one state at first, and then based on this state, you want to do the optimal action, and then the state changes, and then you're going to take another action, and the state changes, and you're going to take another action, and so forth. That's why in this case, when you are doing the training with these kinds of equation, and then when you put one state, then your action will be here. So you're going to put a lot of data here, state and action. So you're going to put a lot of state in X space. you're going to put a lot of state in X space, and then you're going to put a lot of optimal action in Y. Then these kinds of parameters will be trained in order to derive optimal actions. So then once we are done for the training, when we have the other state, then we can estimate or we can infer optimal action. That is called deep reinforcement learning. Okay. So in reinforcement learning, when you have one state, you have to derive optimal action. The deriving procedure will be approximated with this given neural network architecture. So when you study about the Q running or something like that, then you always see this sentence that is called approximate Dq function, which means that Q function means the reward function. Okay, so in this case, you have neural network architecture, you have a lot of states, and then you're gonna have a lot of values, and then when you pick the maximum value, then it will be the action which can guarantee the maximum reward. So this is the training procedure with a given state and action. So then once we are done for the training here, so in this case, when you have a new state, then you're going to do the calculation in order to derive a maximum reward, and then you can take this action, and that's it. That is called approximation of the Q function, and this is DQN, Deep Q Network. The last neural network you have to understand is GAN, Generative Adversarial Neural Network. So in this training, you have generator, you have the discriminator. Discriminator is just doing the classification. So generator will make any kinds of output data. For example, in this case, generator will make a fake sample. So for the first stage, for the earlier stage, generator just making very simple, vague samples at first, and then discriminator can easily find whether this is real or fake. Once we have done this competition, then generator will be able to make better samples. That's why eventually its performance will be improved a lot. So in that case, discriminator should improve its performance as well in order to distinguish clearly. That's why they will gonna do the performance improvement in both sides by competition. So that is called generative adversarial neural network. So let me think about this. Let me talk about this some more details. Let me talk more details about this architecture. So in GAN architecture, you have a generator. This one will make a fake sample. So this one will make a fake data, and discriminator, this one knows what is the real one. So then, since this one knows the real one, it can easily do the classification. Okay. So discriminator knows the real one, and then if this one has the fake sample, it can say that this is fake, this is real, because it has knowledge about the real world data. But generator does not have any kinds of information about the real data. It just make a fake sample. Okay. So discriminator is just a simple binary classification. It just make a classification whether this is real or not. So this is very simple binary classifier, and it has input data, it has output, labels. That's why we are saying that this is supervised learning. But as you can see here, generator has no input. Okay, it just make a fake sample from the random noise. That's why this has no arrival or no input. That's why we are saying that this is unsupervised learning. So in this slide, the orange image called a fake. Okay, this is fake sample. Okay, so generator will always make fake sample. Okay, from the random noise, since it has no arrivals. As you can see here, it has no input. It has no input. That's why we are saying that this just accept noise data. So this one has noise data, and this one will make this fake sample. But the generator's objective is that this one will be converted to probability distribution, just like that. So this one, the red one, will have these kinds of probability distribution based on this pixel density. So we know the real data in this case, and then we wanna make the fake data which has very similar probability distribution with the real data. If they are almost same to each other, then we can believe that this fake data is very similar to this real one. Okay, this is our objective for training these kinds of generator model. So when you look at this GAN paper or manuscript, you will gonna see you will always see the objective function just like that. But as you can see here, it's not easy to understand. That's why you have to split this one, okay? So this slide is for the objective of discriminator. So now you always think about the discriminator in this slide. So we have check mark here. That's what, so it means that you will talk about discriminator in this slide. That's why D means discriminator, G means generator. Since this slide is for the discriminator, you don't need to worry about this one. Only focus on this one, maximization of this given value, okay? So you want to maximize this one. So as I told you before, discriminator is just a simple binary classification. When this one accepts real data, it should return 1. When this one accepts fake data, this should return 0. That's all, okay? So suppose that we have real data, just like that. Then this discriminator will return number 1, should return number 1. When this discriminator takes fake data, then this should return 0, right? So that's our main objective. So suppose that our discriminator is also neural network. That's why I put NN here. I put NN here because this is also a neural network architecture. So this capital X means real data. That's why when you take capital X in capital D function, then this should be high, close to number 1. This is our main objective. So then you have this one, okay? When you have D over X, this should be high. That's why we want to maximize this one, okay? So let's look at this one in this right-hand side. In the right-hand side, our discriminator take the fake sample. As I told you before, fake sample is the return value of our generator model. So this is our generator model with neural network architecture. It has random noise. That's why I put this one just a small g. So this function takes small g and make fake data, okay? That's why g of g means fake data, okay? Then our D function, discriminator, take g of g, then it should be very low. You understand what I'm saying? Okay? So that's why I put just like that. D of g should be very low. That's why 1 minus this one should be high. That's why we want to maximize this one. Okay? So this is the training result when we accept real data. This is training result when we accept fake data. Okay? When you add it to each other, and then we're gonna get some value, and then we wanna maximize this one. This is the objective function of the discriminator. Okay. Now it's time to see the generator's objective function. Okay. So in generator, as I told you before, it has no input. That's why it has no chance to look at real data. So in generator, it has no chance to look at the real data. That's why we cannot consider this case. So please forget about this one. That's why we don't have this one. So in this case, the generator's main objective is that we wanna fool the discriminator. Okay, we're gonna make a fake sample, and the discriminator should think that this is real. That's our objective function. That's why generator will make a fake sample at first, and this one will be allocated to our discriminator function, and this should say that this is real. This is the main objective of the generator. That's why D of g should be 1. This is the main objective function of the G function, okay, generator. So here, 1 minus D of g should be very small, okay? That's why we want to minimize this one. This is the objective function of G. So this is talking about that. So this is the gain function. So G is also neural network. D is also neural network. Your generator is neural network. D, your discriminator is also neural network. The main cost function of the G is that you will gonna make a fake data, and then when you take this one in D function, it should be small because it should be very high because it has to say that this is real. This is the main objective of generator. In previous slide, the main objective of discriminator is that when this one take real one, then this one say that this is real 1. When this one take fake data, and this one should say that this is 0, fake. So based on this fact, we can make the objective function of each neural network, and this can be converted to the cost function, and then we can eventually conduct the training in both sides. So this is the main logical flow in generative adversarial neural network. Okay, so up to now, we understand the basic numerical procedure for the deep neural network, and then we briefly understand what is the CNN, what is the RNN, and then lastly, I told you about the GAN architecture, which is widely used for a lot of applications. The reason why GAN is important is that the result value of the GAN is another data. So up to now, in neural network, our result is just the classification result. This is apple, this is banana, this is something. So all the neural networks results are labels. But now in GAN, our result is not a label, it's the data again. That's why GAN is nowadays very powerful, because it can make a lot of data based on the given training sample. That's why this is important. So up to now, we studied about the basic neural network architectures. So from now on, I would like to introduce more details about the applications of the deep neural network in communication networks or computer networks. 다음 slide. From now on, I have some more fun stuff. So first of all, I briefly introduced what is the deep reinforcement learning before. So from now on, I will gonna describe more details about the deep reinforcement learning, and later I will gonna briefly introduce what is the federated learning. Okay. So reinforcement learning. So reinforcement learning has a long history. So the term reinforce is used. Professor Marvin Minsky's PhD thesis in 1954. So Professor Marvin Minsky is the pioneer in deep neural network as well, because he invented hidden layer architecture. That's why he is a very big guy. In his textbook, which is called Perceptron, published in 1969, it introduced the hidden layer architecture. And 15 years ago, 1954, he received his PhD, and this is the title of his PhD dissertation. So here he started to use reinforce, the term of reinforce from the time. That's why it has a long history. It is analysis with animal learning and psychology, and one of the most successful application of the reinforcement learning is NASA space mission. And when I was college students, university students, there are a lot of 동아리 clubs. Those are talking about the robot soccer. So robot soccer is one of the big successful applications of reinforcement learning. Okay, so then, but we have to understand when reinforcement learning can be used. So it is for finding the optimal action sequence. Not only, this is not for the single one-time solution. We have to find the action sequence. Okay, when you want to escape from the maze, then you have sequences, right? Action sequences. When you want to do the space mission, it has action sequences. When you want to do go play, then it has a sequence, because you have to put one action and then state changes, then you're going to put another action and so forth. That's why it has action sequence. So when you have action sequence, then you have to use reinforcement learning. And your action is for maximizing your reward. Okay, so you're going to do optimal action, and then eventually you're going to get the result of the reinforcement learning computation. The reinforcement learning, one of the simplest reinforcement learning algorithms is Q-learning, and another one is Markov distance process. Those are all very simple, and then these are all based on the recurrent. That's why they can be solved with dynamic programming. So in a lot of papers, when you study about Q-learning or Markov distance process, then eventually you can read one sentence which says that these kinds of framework can be solved with dynamic programming. But when you look at dynamic programming, you have to understand the computational complexity. The complexity of the dynamic programming is pseudo polynomial. It means that when your given state is very small, then you can solve the problem, you can get the optimal solution in polynomial time. That's why you have no problem at all. But if you have large size state, then since this is for pseudo polynomial, you're gonna get some experience with high computation. That's why you will be that's why you need a lot of resources in order to solve the problem. That's why we have some challenges when your state is very big. Okay. So the only thing when you read the reinforcement learning application papers, when you set appropriate action, when you set related rewards, and that's it. you have some kinds of framework which is for the reinforcement learning formulation. That's why when you define reward and actions, then that's it. It's very simple. However, as I told you before, the issue is that your complexity. Okay? If your state is very small, no need to worry about that. Just use dynamic programming. That's it. But if your state is very big, huge, then you're gonna find another way to solve these kinds of reinforcement learning problems. So one solution in large state cases is using neural network. This slide is obtained from our previous lecture slide. So in last sense, I told you that this can be used for the deep reinforcement learning. So suppose that X is our state, Y is our optimal action. Suppose that we have a billion data, state and action. Suppose that we have billion data, billion number of states, billion number of optimal action for each state. Then in that case, these parameters will be trained in order to derive optimal actions. And then when you have new state, then you can infer new approximated optimal action. This is the basic concept why you are using deep neural network for solving reinforcement learning problem. That's why from that time we are saying that this is deep reinforcement learning, not only reinforcement learning. Okay. So one application is I2V infrastructure, proactive caching. The next example is multi-UAV coordination for 5G network coverage extension. Okay, so the left side. So as I told you before, in order to use the reinforcement learning, you have to set your reward, you have to set your action, and that's it. Then you can directly use the reinforcement learning framework. So here we consider the case of proactive caching. So in this case, vehicles are moving to this direction, and in this case we have infrastructure. Infrastructure has caches. That's why if this one is here, then this will take the video from this cache, and we know that this will eventually go this way. That's why once we are doing the service for this vehicle, then we can put this video data into here after some time spending. So then we have to control the compression ratio of this video, and we have to control the cache size in the next hop. That's why our action is video quality and cache size. And then in order to take this action, we have to set the reward function. So for the reward function, we have a frozenness, which means that when you have to wait some time for playing this video, that is called frozen. And we have to increase our average video quality. We have to minimize our packet drop. This will be considered for reward formulation. Okay, so this is what we did for these vehicular networks. So next one is multi-UAV coordination. Suppose that you are thinking about the millimeter wave 5G networks. So in millimeter wave, especially in 60 GHz, you will have some directional propagation, okay? And then this can be blocked. That's why you have to consider the blockage impact. You have to avoid the non-line of sight, okay? This should be considered. So suppose that this is mobile base station. We want to extend our coverage. Then you have drone here, and this is mobile base station. That's why if it has millimeter wave directional antenna, then it can serve this area. So then we want to find optimal positions of multiple drones. That's our main objective in order to maximize our cellular coverage. So here we have these kinds of cells. We have these kinds of mobile base stations. Drones are flying here. Then this can serve this area. This is directional propagation. If this propagation is blocked, then we have no more service. Okay. So then we assume that our drones has LiDAR sensors. We can do the path planning. Okay. Then our states are location of drone, and our states are degrees and directions of these kinds of propagation because millimeter wave directional propagation. And then in order to this research, we set our action as moving direction and rotations. And our rewards are collision with obstacles, collision with drones. Those are all four negatives. And when we arrive at the destination, we have positive rewards. And when we make more and more line of sight communication, then we have positive reward. Okay. So this is the result. In here, this is our core base station. These are our mobile base station, and they are blocked. So in our initial stage, this one is the base station. That's why this will transmit signal to this user and this user. But as you can see here, those are all blocked. Okay, that's why they have no service. But when drones are here, it means that this base station will give signal to this base station, and this base station will give signal to this user. Then we can establish two-hop line of sight communication. Okay, that's why we can extend cellular coverage with this multi-agent reinforcement learning. But this work was not published because it's very complicated in 3D case. So we start this research at the time, and it works very well in 2D geometry. But in 3D geometry, we have different building heights. We have to model all the urban scenario in a simulator. That's why it is very complicated. So we could not do this one in 3D geometry. However, in 2D, we can see a proper control action for each drones. So lastly, I would like to introduce what is the imitation learning. So imitation learning is quite interesting. That's why I want to introduce what is the imitation learning. So in ICML conference 2018, Professor Lee Seong-yu at Caltech made a tutorial for imitation learning for 2 hours. And when you visit this site, then you can see the YouTube video and you can download some lecture slide. That's why it is very useful if you have interest. So in 2009, you can see another lecture for imitation learning by Professor Sergey Levin at UC Berkeley. And when you visit this website, you can also see the slide and videos. Okay, so if you are interested in, then you can visit. So this is the main application of imitation learning. Suppose that you want to do the multi-agent reinforcement learning. Okay, suppose that you want to do the soccer player with your friends. So suppose that you have 5 friends. Then, including yourself, 6 players are in the playground, and then suppose that every single player is agent, and they want to maximize their reward. In soccer, when you kick your ball, then you will increase your reward. That's why, in this case, if the agents are not talking to each other, then every agent wants to kick your ball. That's why they are not doing the coordination. They are not doing the cooperation. That's why it has some problems. The main objective of multi-agent reinforcement learning is that they have to do the cooperation in order to maximize their ultimate goal. So in order to solve this problem, imitation learning was proposed. So in the left-hand side case, we have 3 players, 3 StarCraft players. And then, in order to let them do the StarCraft, we have to formulate the StarCraft behaviors, but it's not easy at all. That's why in this case, take 3 StarCraft players and let them do the game for 1 week, 2 weeks, or 1 month, and then you will gather all the data. Okay, so then based on the result, here. You will put a lot of state here, StarCraft states here, and in Y is a 3-dimensional vector. Each component has the action of each player. I told you that you have 3 players. That's why 3 size vector will be your result. And then in each element, you will set your actions for each player. And then once you are done for the training with 1 week, 2 week, or 1 month data, then you can derive the parameters which can infer the actions of the StarCraft players with your given state. Okay. So as a result, once you have done your training, when you have new state here, then the neural network make the inference which can define the optimal action for each 3 players. Okay. So that is the main procedure for the reinforcement learning. So when you read the imitation learning paper, this sentence will appear for the first paragraph. The goal of imitation learning is to train a policy to mimic the expert's demonstration. This is not aiming at the optimal result. We have no interest on the optimal result. We just follow the expert demonstration, and that's it. Okay, so that's why I gather all the data every single time. We have no interest on the reward. we do not think about the reward. You just gather the data, you just take the state, and then you just observe the actions. State, action, every single time, you will get a lot of data, and you will put these data into your neural network, and the neural network will be trained, and then when you have a new state, then you can infer to new actions. That's it, okay? That's why we have no interest on the optimality, you have no interest on the reward, just follow what they did. And that's called imitation learning, okay? The reason why imitation learning was proposed is that actual reward shaping is very hard. So when you want to use reinforcement learning, you have to set the reward. That's why based on the reward, you can define your action. However, finding actual reward is always difficult in real world applications. That's why you don't need to think about the reward from this time. You just follow what they did, and that's it. That's why imitation learning is generally used. The next reason why reinforcement learning is difficult is that safe learning is not achieved in general reinforcement learning. So suppose that I drive from Korea University to this Yongpyeong. So in this case, if I want to maximize my reward, then I will pursue to arrive here as soon as possible. Then my driving will not safe at all. It just control, and it just want to go as fast as possible. But if we are doing the imitation learning, this vehicle will learn as people usually did. Okay, that's why safe learning can be achieved with the imitation learning. So imitation learning handles with these problems through the demonstration of the experts. Okay. Then from now on, we have to think about the history of the imitation learning. So do you know Professor Andrew Ng, which is very famous professor in Stanford University? Then do you know the PhD dissertation of the Professor Ng, Andrew Ng? So Professor Andrew Ng at Stanford wrote his own dissertation, maybe 2001 at UC Berkeley, and the topic was inverse reinforcement learning. This is the origin of imitation learning research. The idea is very simple. So upper side is our simple reinforcement learning. We already know what is the reward. Based on this reward, we're gonna make an action which can maximize the reward. That's the basic concept of the reinforcement learning. But inverse reinforcement learning is opposite. So it does not have information about the reward at all. So suppose that I want to follow maybe Professor Ng, okay? Then I will observe Professor Ng's behavior. And then inversely, I want to calculate his reward function, okay? So here, we will observe expert policy. I will observe Professor Ng here. So then we have expert trajectories. So Professor Ng has states as sub-zero, and he is making an action just like that. He moved to the other state, and then he made another action. He moved to the other state. He made another action, and he moved to another state, and so forth. I will observe this trajectory. And then I will try to understand his inside reward. Okay, so the main solution of inverse reinforcement learning is the R values here. Okay, I want to calculate reward value within Professor Ng's behavior. Okay, so in upper side, in conventional reinforcement learning, then we know reward value at first, and then we take the action. But in below, oppositely, we observe his trajectories, and then I want to understand his reward value. And then if I can calculate the reward value, then I can act just like him. That's called inverse reinforcement learning. So in his ICML paper, during his PhD, he proved that it is possible. We can calculate this one in polynomial time based on the quadratic programming optimization, which is very similar to support vector machine. Okay, so that's what he did when he was PhD student. Okay, so this one is the origin of the imitation learning. From that time, people want to understand the behavior of this agent. But at his age, 1999 or 2001, we had no concept of the multi-agent reinforcement learning at the time. That's why this framework will not work at multi-agent system, but it shows some origins for the possibility. one of the simplest algorithm for the imitation learning is called behavioral cloning. Okay, behavior cloning. This is very simple. So here, so red ones are expert action. So this is our aim. Okay, we want to follow expert action. So these are all our real values. And here you have blue letters. Those are all called policies. Okay, so pi means policy, and you have these kinds of parameter, which is called neural network parameter. Okay, so pi sub theta means that this is our policy derived by neural network architecture. Okay, then in this case, you want to train the neural network. Okay, so now, as you can see here, you can simply understand that this L function is simple mean square error. Okay, so here this is our aim. We want to train this neural network for policy when we are in state S. Okay, and in that case, we have gap between with expert. So we want to minimize this one. Then our neural network will be very similar to our expert. Okay, so that's why we want to minimize these kinds of difference or gap. And then we have square in order to eliminate the sign. And then we want to minimize this one. Okay, so here we want to minimize, and we want to find the argument, which is theta. We want to find the theta, which means that we want to do the training because we want to find the parameters of the neural network. Okay, so eventually, based on this equation, we can say that this says that okay, we want to train our policy with a deep neural network at given state S, and we want to take the parameters which can infer our action, which is very similar to expert action. And that's it, okay? So this is very simple description. And this is one of the simplest algorithms in imitation learning. So this is StarCraft example, what I saw you in previous slides. So in here, our state is minimap, StarCraft minimap, and screenshot. Okay, and then we understand the players' experts' behavior. They will gonna select some unit. They will drag them to move them to the other space. That's why these are our actions. And then we have state and action from our expert programmers. And then we will get a lot of data. And then based on this data, and then we want to train our policy. And then once we are done for the training and given state S, we can infer our optimal action. And that's it. This is imitation learning procedure. So when you search imitation learning in Google search engine, then the related keyword is autonomous driving. So when you want to do the autonomous driving research, then imitation learning is one of the major algorithms in the society. So when you are driving, you have sensors in your car, LiDAR sensor, millimeter wave sensor, or front-head cameras and so forth. So you will get a lot of data. So states are your sensory data, okay? And then it will observe the actions of the driver. I can push my brake, or I can steer my wheel, and I will get the vehicle will get that kinds of data. So then, okay, there is one people, this is called Kim 중헌, and Kim 중헌 is driving, and in Kim 중헌's car, it has some sensory data, and with this sensory data, he is doing some wheel steering and brake pushing or something like that. We get all the data from the expert. So we get all the data from expert, SNA, and then based on that, we are gonna do the training with the deep neural network for the policy when our given state is S. Then we can infer our optimal action A, which is very similar to Kim 중헌's driving behavior, okay? But here we have some intuition. So imitation learning is for expert, okay? My car will be driven by myself only, okay? My wife is not driving. My babies are not driving. That's why my vehicle is only for me, okay? So then it can understand some specific actions. But suppose that my car is driving by hours, and then it will get a lot of actions. Then our action space will go to, which converts to normal distribution, Gaussian distribution. In that case, doing imitation learning has no meaning because we can just pick one action from Gaussian distribution, okay? That's why imitation learning is only for the expert system. The system which is dominated by specific users. So imitation learning is only for the applications, okay? Suppose that you have a PC방, you have some PC shop in your university, so then the computers in the PC shop will be used by all the students in the college. So then the actions in the PC has no meaning because it already converts to Gaussian distribution, okay? So you have to understand that imitation learning is for the expert system or dedicated system. So I made one idea simply. Suppose that, so the one device which is used by myself is smartphone. Smartphone is one of the most popular example, which is very privacy preserving device. Okay. So suppose that I want to do the authentication in order to use my cell phone. And then, the cell phone knows my cell phone usage behavior. I use KakaoTalk, I use Facebook, I use YouTube, and so forth. It also knows my using time and using sequence or something like that. Then the cell phone can understand my behavior. So here, our states are usage, and action is my use patterns. Based on that, this cell phone can understand my behavior. And then suppose that someone knows my passcode, then they can get into my cell phone system. However, this cell phone can say that, okay, this user's behavior is not similar to Jungwon Kim's behavior. That's why I'm gonna block this guy. So we can do that, okay? This is AI-based security system. This is imitation learning-based security system, okay? So I made this idea. This is my idea. I made this one. So I let my son do this one maybe 1 year ago, but he graduated. That's why we have no result yet. So if you have interest in, you can try. This is project with the Seoul National University Hospital nowadays. So 마취를 영어로 뭐라 하지? 마취과. So in some department of this hospital, we have some, so there is one doctor over there. He has a lot of data. So this is BIS, blood pressure. This is kinds of state of human body. Okay. And then they have to inject some medical stuffs into human body. So this is a propofol. This is remifentanil. These are for the medicine which are using during the surgery. So doctors are putting some medical stuffs into human body during the surgery in order to remove the pain from the human body. That's why based on the BIS value and blood pressure value, they are controlled the amount of the medicine injection. Okay. So the doctor said that Seoul National University Hospital has the data which gathered for 4 years in 31 surgery spaces. That's why they have huge data. Based on the data, we are doing some training. That's why we are designing expert system which can act similar to doctors over there. That's why we are doing this research nowadays. But this is not easy at all because in reinforcement learning, we observe one state. Okay, we observe one state at first, and then we made one action, and state changes. But in human body, we are taking one action such as propofol injection, and then in order to change the state, we need some time. Okay, because human body is a delayed system. So we inject some such amount of the medicine, then we need some time in order to spread this impact and in your entire human body. That's why we have to wait. Okay, but we don't know how much we have to wait. That's the main issue over there. In addition to that, these kinds of medical injection has some correlation. If you put a lot of propofol injection, then we have to reduce the injection of the remifentanil. So they have some correlations between them. That's why it is not easy. Okay, but eventually we are done for this project and we submit one paper based on this result. So after doing some IRB certification at the hospital, we want to use this system in real-world surgery procedure. So this is the autonomous driving applications with imitation learning. So this is paper which published last year in our research lab. So we get a lot of expert data. So based on this expert data, agent can do the training. And then, so in neural network training, we are doing gradient descent optimizer. In our first slide, I told you that we have optimizer in neural network procedure. But the optimizers are all based on the partial derivation. partial derivation takes a lot of time, okay? In order to speed up the neural network architecture training, we are using multi-core system or something like that. We are using GPU, we are using multi-core systems, but conducting partial derivation calculation procedure in multi-core system is not easy. So suppose that we are all processors. And if I have one problem which have to do the partial derivation, then we cannot split this problem for all of us. Maybe one or two people are solving that problem. The others are not solving anything. Okay, so it's very difficult to do the parallelization. So in that case, we have a new approach. So here we have random sampling. It means that if we are all processors, I told you that okay, each processor should make 1,000 samples randomly. Then I can get all the data eventually. Then we may have 100,000 sample. Among these 100,000 sample, we have one discriminator, which is for GAN, and this has discriminator. It means that this can pick only one, which shows the best sequence. If then the result might be better than the partial derivation result. That is the experimental result in this paper, and it shows that that is slightly better than our previous deep reinforcement learning sequences. That's why we propose these kinds of random selection based, random selection and game based imitation learning for autonomous driving. So based on the result, we implemented the system, and here the red car is our autonomous driving vehicle. So if this one has conventional reinforcement learning, it will pursue the maximization of the reward function, which means that it will change the lane a lot in order to speed up. But if it works similar to human being, then they will change the lane slightly, right? That's why, as you can see, red vehicle, it is changing the lane slightly, not frequently, okay? So now let me briefly introduce what is the federated learning. So as I told you before about neural network architecture, I told you that we need a lot of data. We also need a lot of labels. That is basic assumption for our neural network training. But gathering all the data in a single storage is not easy, right? So suppose that you have hospital networks, just like that. So suppose that you take X-ray or CT in this hospital A. But taking the information from here and gather all the data at a single space is not allowed by the law for the patient privacy preserving, okay? That's why each hospital should conduct its own training at first, and then they have to aggregate all the parameters in order to construct global neural network model. So in medical platforms, we cannot share patient data because of privacy issue, okay? But in wireless system, so suppose that you have drones and they are used for the surveillance applications. So in that case, they will gather all the image data. But while they are gathering all the image data, but aggregating all the data in a single space takes a lot of communication overhead. That's why here it's very hard to share the UAV data due to communication overhead and reliability issue. Okay, that's why each drones or each UAV should conduct its own training at first, and then they have to aggregate all the parameter, and then we have to construct global model based on the result. Okay. So we have more and more challenges in federated learning. So in medical applications, it is much more serious. So here, suppose that this hospital is very famous at plastic surgery, for example. So this one is very famous at plastic surgery. So then many patients will be here, and small number of patients are here as well, right? So as I told you before, when I introduced overfitting, when you have small data, then you have overfitting. So this hospital may have overfitting parameter. This hospital has overfitting. This hospital has enough data, that's why it's fine. So in this case, overfitting may happen in some models. That's why eventually we have to aggregate all the parameters from here, but the parameters from this hospital and this hospital is not good at all. That's the main issue in federated learning in medical applications. So next one is to duplicate data. Suppose that I'm doing some exercise in this hospital and the result is not that good. Then I'm worrying about that too much. Then I may visit the other hospital in order to check that I actually have that disease or something like that. Then I will visit this hospital, I will visit this hospital, I will visit this hospital. And then, since the hospitals cannot share the patient information, as I told you before, because of the privacy issue. So in the case, there is no way to check whether there are duplicated data. If you have duplicate data, then the training result will be biased. That's why it has serious issue in medical applications. So then we may have duplicate data. It may introduce training performance degradation. Lastly, data aging. So here I took some exercise. The result is not that good. That's why I want to visit the other hospital. I will make another reservation. And then 6 months later, I take another exercise here. Then if my development of the disease is so fast, then the behavior in here and here, behaviors will not same at all. Okay, but the development of my disease is very slow. Then the data here and data here will be same to each other. That's why this is one issue about in this system. So when I doing this project with the Seoul National Hospital and Jungwon University, so the modeling of disease propagation or disease development is doing by Professor Im Ye-ji at Jungwon University Statistics Department. So the professor over there is doing the research for this kinds of differentiated aging of the disease. But up to now, we talked about the medical applications. But from now on, I want to talk about the communication systems. Suppose that we want to do the federated learning. So we have multiple users here. This is device 1, device 2, device 3, and so forth, device K. And each devices are conducting its own neural network architecture training. So you have trained result here, you have training result here. And then they have to upload their own data into your edge server or cloud server over here. So in the case, they are using dedicated bandwidth in order to avoid the interference to each other. So then it will get all the data, and then they are making global model here. But as you can see here, it just uses a simple summation. But maybe you are not agreeing with this one, right? So in medical applications, as I told you before, this one has overfitting data, this one has overfitting data, this one has very nice weight factor. But when we are doing just simple averaging, then the global model is worse. Okay, that's why maybe you may not agree to this result. However, in initial phase, we used this kinds of the aggregation. This is called federated averaging. But basic assumption of this paper here is that each device are generating its own data based on the sensing, based on the camera capture or something like that. So basic assumption here is that each device can generate its own data based on the sensing. But in hospital data, patients should be there. If a patient is not there, then we cannot generate any kinds of data. But in this case, if our data is not enough, then we can make new data. That's why the basic assumption in this paper is that we can avoid overfitting in general, okay? But in order to handle that issue, we have another paper, this one, that is called weighted averaging. So here we have one weight in front of this parameter, which is called capital D. The capital D means the number of training data in order to make these kinds of W parameters. So here, so in this example, let me explain with this example. If you want to do the weighted federated averaging, suppose we have to consider this value 10, and 1000. We have parameter here, we have parameter here, we have parameter here. In our conventional federated averaging, we just take the average of them. But now we have to do the weighting. So since it has 1000 data, then the weight factor here will be multiplied with 1000. Weight factor here will be multiplied with 10. Weight factors here will be multiplied with 10. And then we agree all of them. We are doing the aggregation with all of them. And then we will gonna divide by 1020. Then we can put more weight on top of these kinds of data, these kinds of model here. If we have small number of data, then the weighting should be reduced because it may be overfitted. Right? So by doing these kinds of weighting, we can eliminate overfitting models from the general model. Okay, that is called weighted federated averaging. So next one is for the attention model. So suppose that we have a multiple federal learning devices, and then we have weight factors for each federal learning user devices, local devices. So then, based on the attention model in natural language processing, we can dynamically control the weight for these federated users in order to make optimal global model. Okay, so that is proposed by natural language processing guys. And then the paper name is Learning Privacy Neural Language Models with Attentive Aggregation. So this is the first paper which is using attention model in order to make general global model from federal learning devices. The next one is mobile edge computing based federal learning. So in this case, the last one is our conventional federal learning. So here, local devices are doing local training, and then they are uploading their model parameters, not the data itself. So this one is uploading parameter, this one is uploading parameter, this one is uploading parameter, and they are doing the federated averaging or weighted federated averaging or attention-based federated averaging. So then they can infer the global model, okay? The middle one is not federated learning. They just upload data, and then the cloud will do some training with global data. The last one is the federal learning with mobile edge computing. So in that case, this can be used for the conventional LTE or cellular networks, and the cell phone will upload its own data at first, and the base station, it has edge device, it has low-level neural network architecture training at first, and then the last mile high-level training will be conducted in the cloud. Then the past information from here to here will be the weight factors. That's why we can keep the privacy preserving by doing this kinds of two-stage training procedure. So this is edge computing, this is cloud computing. That's why we can have these kinds of architecture if you want to do the federal learning in mobile edge computing environment. Yes, so on top of this one, we have another architecture. So I may miss a slide here. So in this case, they are doing their own parameter training at first, and then they are uploading their parameters, okay? And then they can hide their information, their data. They are not exposing their data outside. So that's why they can keep the privacy. Also, they can minimize the communication avoid. But sometimes we have another architecture. So in here, you have input layer, you have output layer, you have 4 hidden layers, okay? But sometimes this one has only first hidden layer and output layer. The other layers are here, okay? So in the case, you have long neural network architecture, you take the input layer, you take the output layer, and then you can make this kinds of way. And then this is your centralized training space, okay? 다시 한번 주시겠어요? Yeah. So here, these users just take input and first hidden layer and output, and it has a portion of the hidden layers, and then this kinds of edge server has a portion of the hidden layers, and then the neural network will be splitted. That is called split learning. The origins of this split learning is proposed by MIT Media Lab, and they made this architecture in order to conduct privacy-preserving deep learning. Okay, so then if it has only one input layer and only one hidden layer here, then they will pass parameter which is the result of the hidden layer. Then they will have a one-dimensional vector. They are not exposing its own data. They just pass the first hidden layer. They will be encoded. Okay, and then they will pass this one-dimensional vector into this edge server, and then they will gonna do the calculation with the second hidden layer, third hidden layer, fourth hidden layer, and the result will be back to this user device, and they have last output layer. Then they are not exposing its own data. Okay, they just pass parameters for the first hidden layer, they just parameter for the last hidden layer, and that's it. But the problem is that in neural network architecture training, we have a backpropagation, which means that in last output layer, we have a partial derivation with gradient descent optimizer, and then the result will be propagated from the last layer to the first layer. And that kinds of backpropagation will be conducted from here to here at first, and then eventually here. These kinds of procedure will be conducted based on the number of training data. Suppose that we have 1,000 training data, and then we have to conduct these kinds of backpropagation 1,000 times. Then we need 1,000 time communication over here. It has one disadvantage of these kinds of split learning. However, at least it can guarantee the privacy of the data, and then we can do the federated learning just like that. But in this case, it has a second hidden layer, third hidden layer, and last hidden layer. It only has first hidden layer and out layer. That's why we had a certain amount of performance degradation. However, model here is global model. That's why performance with split learning is the best comparing to the other type of federated learning architectures. That's why nowadays we are start to think about these kinds of split learning. However, it takes a lot of time because of backpropagation. As I told you before, in medical applications, we are thinking about the hospitals. We are thinking about the Asan Hospital, Bundang Hospital, or something like that. They are all geo-distributed. It takes a lot of time for the communication. We have to conduct these kinds of backpropagation in nationwide networks. It takes a lot of time. That's why it is one issue when you are doing these kinds of split learning. Okay. So in this second lecture, I briefly introduced what is the deep reinforcement learning and what is the application of the deep reinforcement learning. So among a lot of deep reinforcement learning algorithms, I introduced what is the imitation learning. So imitation learning is very useful because we don't need reward value at all. Just we know state, just we know related actions, and that's it. Based on the data, training data, we can make a neural network, and then when you have a new state, then we can infer optimal action based on the expert demonstration. That is the basic concept of the imitation learning. So we can also do the multi-agent reinforcement learning with this imitation learning. So after introducing the imitation learning algorithm, I introduced two network applications for the deep reinforcement learning. The first one is proactive caching in vehicular networks. The second one is UAV coordination in order to extend the 5G network cellular coverage. And after that, I simply introduced what is the federated learning in two applications. The first one is medical application, next one is communication applications. The reason why federated learning is difficult is that in medical application, we have data imbalance, we have data aging, we have what else? Duplicate data. That's why doing federated learning in medical applications is not easy. In communication networks, it's much more easier because we can assume that we have no overfitting because communication user device can generate its own data with the sensor information or something like that. That's why it is easy, but the method in order to construct global model is not easy. We just introduced the federated averaging, which is just a simple average, and then we proposed another algorithm that is called weighted federated averaging, depending on the number of training data. Lastly, we applied attention model for doing federated learning efficiently. And then I just introduced simple network architecture that is called split learning, which can divide the neural network into two parts, which is very powerful, which is efficient, which is very powerful in terms of the performance, accuracy. However, it's not good in terms of the communication overhead. So this is the current research status in federated learning and deep reinforcement learning. Thank you for listening to this presentation. So if you have any questions, please let me know. Thank you. 연습을 하나도 안 한 티가.
저는 영화를 보고 갔다가 뭐야